Hello students, welcome to this lecture on the subject of advanced semiconductor devices KEC 056. This is lecture number 9. I am Dr. Raman Kapoor, Associate Professor at ABES Engineering College, Ghaziabad. In today's lecture, we are going to discuss some specific properties which are related to semiconductor materials, and we are going to see what happens when we create a junction between two similar or dissimilar semiconducting materials. Okay. So, let us start. There are a lot of properties of semiconductor materials which play a very important role when these materials are actually used to produce devices. Okay. So, these properties are usually the signature of that material which is being used as the active material in the device. By active material, I mean the material which is going to produce the actual conduction or the actual operation inside the semiconductor device. Okay. Major properties can be categorized into material properties, optical and thermal properties. Okay. And different semiconductors will have different level and different degree of these properties, and once they are used in a device, the eventual performance is going to be directly or indirectly dependent on these properties. So, the aim of this lecture is to identify these properties and study them in greater detail. Okay. We start with the material properties first, which are usually described in terms of what is known as Phonon behavior or Phonon spectrum. Okay. In our discussion on mobility, we had seen that when extra energy is provided to a semiconductor, that energy can either get consumed by the movement of charge carriers, and if there is some excess energy available, that can be absorbed by the immobile atoms or ions, and they dissipate this extra energy in terms of vibrations. These vibrations manifest in terms of lattice vibration known as phonons. Okay. So, phonons are nothing but the quanta of lattice vibrations which mainly result from thermal energy provided to the crystal lattice. Similar to photons and electrons, photons is packet of light, electron is your atomic charge carrier. These phonons, since they are associated with lattice vibrations, okay, they have a certain characteristic frequency, okay, and since they have a wave like behavior, they also have an energy associated with them. And if they have a frequency, they have energy, they are bound to have a wave number which can be used to identify the momentum or wavelength. Okay. So, in a one dimensional lattice structure where there are only nearest neighbor coupling. Okay. So, two atoms or ions, they are the nearest to each other. So, they can be considered to have a sort of a coupling between them, and they possess different masses m1 and m2. Okay. So, this mass here can belong to an atom, it can belong to an ion, it can belong to any identity which is vibrating inside the lattice and producing phonons. Okay. So, the frequency of oscillation in such a case is given by this large equation which you see on the screen. The equation might seem large, but the number of parameters are not that large. Okay. So, you have the mass of each neighbor. Okay. You have two parameters alpha f, k and a, we are just going to discuss them, and you see that there is a, if you see this symbol of frequency, there is a plus minus sign here. This basically means that there are two modes associated with the phonon spectra. Okay. Alpha f in this equation is known as force constant of Hooke's law. Okay. So, whenever there is a mechanical vibration or a mechanical movement, the force which is being applied and it produces a displacement, they are proportional to each other, okay, and that proportionality constant is a certain value like spring constant or force constant. Okay. K subscript ph is the phonon wave number, the so called k value, okay, and a is the lattice spacing, the spacing between the two nearest neighbors in a three dimensional crystal arrangement. As I said, there are two possible modes denoted by this plus and minus sign here. The minus sign, so frequency V nu minus is proportional to this wave number, okay, as this wave number approaches 0. So, for lower values of wave number, this mode of frequency is proportional to it. This is known as the acoustic mode or acoustic branch. Okay. And the other mode nu plus, it tends to be a constant as your wave number approaches 0. So, you can say that it is more or less independent of the wave number. Now, wave number is a measure of momentum. Okay. So, that is why one of the mode is known as acoustic and other is known as optical. You see, the optical mode has nothing to do with momentum. So, that is why this mode is usually independent of the wave number. Okay. So, for the acoustic mode, your nu minus, which is proportional to the wave number, the two sub lattices of the atoms with different masses, okay, they move in the same direction, while for the other mode, the optical mode, they move in the opposite directions. The total number of acoustic modes is equal to the dimension times the number of atoms per cell. So, if you are looking for a one dimensional structure or a two dimensional or a three dimensional structure, the number of acoustic branches or modes is going to vary. So, for typical three dimensional lattice structure with one atom per primitive cell, your basic unit cell structure, you can have 3 acoustic modes. Okay. And for a 3D lattice with 2 atoms such as silicon or gallium arsenide, your elemental and compound semiconductors, 3 acoustic modes and 3 optical modes tend to exist. Okay. So, these can be studied in greater detail to identify what kind of material properties we might see once these materials are used in devices. Okay. So, this is related to the Phonon spectrum or material properties associated with a semiconducting material. We now move to the second category. This is related to the optical behavior of semiconductors. Okay. As we know that semiconductors are characterized by a moderate value of energy band gap, and that energy band gap, the distance between the end of valence band and the start of conduction band, it plays a lot of it plays an important role when it comes to the optical behavior of the semiconducting device. Okay. The amount of energy generally emitted, if it is in the form of light, is proportional to the amount of the level of energy band gap. Okay. That forms the basis of many light emitting diodes. So, this analysis, optical analysis, it constitutes a very important way of determining the band structure. Okay. So, as I just discussed about energy band gap, the optical behavior tells you a lot about the band structure of a semiconductor. Okay. If photons are incident on a semiconductor, it is going to provide extra energy to those electrons which are present in valence band. They might get excited with this extra optical energy, and if this energy h nu is at least equal to the energy band gap, you are going to see a generation of charge carriers from the valence to the conduction band. Okay. And once they move back via recombination, okay, that amount of energy dissipated, if you measure the wavelength of it, it can help you to measure the energy band gap. Right. The optical properties of semiconductors, they are characterized by the refractive index, which is a complex number. So, this is a refractive index, it has a real part, it has an imaginary part. Okay. The real part, it determines the propagation velocity and wavelength of light in that particular medium. So, how fast and for how long the optical energy travels, okay, or the optical light travels in the semiconductor, that is decided by this real part of the refractive index. The imaginary part, k subscript e, is known as extinction coefficient, and it determines the very important property known as absorption coefficient. This basically measures the distance. Okay. So, you can see that k and lambda are actually related to each other. Right. So, this basically measures when light is incident on a semiconductor, how far it can travel before the intensity dies down. Right. So, the major optical properties for any semiconductor can be measured by this refractive index, and it provides you two informations. one related to velocity and distance and another related to absorption coefficient. Okay. The absorption coefficient, which is a strong function of wavelength, you can see that alpha is proportional to 1 over lambda, okay. And lambda is inversely related to the energy of the photon. So, you can say that this absorption coefficient is directly dependent upon the amount of energy incident on the semiconductor. Near the absorption edge, that is considered in the points of view of the distance, you can consider at this as the start of your semiconducting material, the point at which the light starts to become incident. Okay. The absorption coefficient is proportional to h nu, the incident energy, minus the energy band gap. Okay. So, because you need at least a minimum level of incident energy, so that you can have some kind of a generation taking place, right. So, this incident energy minus the energy band gap, plus there is a constant parameter known as gamma. Okay. If it is 1, then you can directly say that the amount of difference in energy is deciding your absorption coefficient, but for certain materials it may not be equal to 1, right. So, optical properties, they play a significant role. They help you in differentiating whether the semiconductor is going to be radiating or non radiating, whether it is going to emit light or it is just going to dissipate heat. There are two types of band to band transitions. When we talk about band to band transitions, we actually either mean the valence to conduction band transition or conduction to valence band transition. For radiation properties, we are more interested in the opposite, when carriers move from conduction to valence band. Okay. The amount of energy they release is equal to the energy band gap. So, you have two type of transition, one is known as allowed, another is forbidden. The so called forbidden transitions, they take into account the small but finite momentum of photons, and the probability of this forbidden transition is actually less, right. And the so called direct band gap materials, we have had a small discussion on this before, direct and indirect semiconductors. In direct band gap materials, these transitions mainly occur at the same value of momentum. Okay. So, if a electron is at EC, it makes a transition back to the valence band, right. If it does not lose any momentum, it dissipates energy in the form of light, and since k, the wave number, is a measure of momentum. So, you can say that the value of momentum remains same at EC and EV. This is a direct semiconductor, it releases light. Okay. This is what is forms the basis of a light emitting diode. Okay. So, direct transition can occur in all values of k. Forbidden direct transition can only occur when k is not equal to 0. So, these are generally your excited charge carriers with non-zero values of momentum. When k is 0, okay, in your EK diagram, your so called center point in the EK diagram, the band gap is defined at this point, right. The only allowed transition occurs and it is used for measuring the energy band gap. Okay. So, you can say that this at k equal to 0, this distance is your energy band gap. If the value of momentum remains same, it is direct recombination. If it is not same, it is indirect recombination. Okay. The absorption coefficient now becomes slightly different. Okay. Now, apart from optical properties, you can also have properties related to the thermal nature of semiconductors. When semiconductors are heated, different semiconductors react differently. Some may have high thermal integrity, some might have very low levels of thermal conductivity. Okay. So, when a temperature gradient exists in a semiconductor, in addition to the external electric field, the total current density in one dimension changes, okay, and it becomes equal to this value. Sigma is your conductivity, right. dEf by dx is the gradient in the energy band diagram, which happens when there is an electric field present, okay, minus thermoelectric power P and the temperature gradient. So, you see electric field gradient with respect to distance and temperature gradient with respect to distance. Okay. So, instead of your general J equal to sigma E, you have a slightly modified equation in the presence of two sources of energy. one being the external electric field and another being temperature gradient. The thermoelectric power is negative for n type semiconductors and it is positive for p type semiconductors. So, once you determine the value of J, you can identify the sign of P. This sign of P basically tells you the polarity of the semiconductor. So, you can identify whether an unknown semiconductor is n type or p type, okay, by seeing the sign of the thermoelectric power P. It can also be used to determine resistivity, right. So, if you have conductivity, you can determine from here, reciprocal of that becomes resistivity, and also the position of Fermi level with respect to band edges, okay. Between E c and E v, you can measure the position of Fermi level, right. Another important thermal effect is related to the conduction or thermal conductivity. It is a diffusion type of a process where heat flow Q, rate at which heat flows due to temperature gradient, is equal to minus, this symbol is known as kappa, and temperature gradient. Okay. That minus sign is basically is indicative that the flow of charge or the flow of heat is opposite to the temperature gradient. So, it flows from higher temperature to a lower temperature. Okay. This is thermal conductivity, the symbol which is written here, this is the known as thermal conductivity, okay. And it has major components, it has contributions from lattice vibrations in the or phonon vibrations in the presence of thermal energy, and free carrier conduction which happens due to this extra thermal energy of the charge carriers. So, total thermal conductivity has two components, one because of the lattice itself and another because of the charge carriers, okay, which may be because of doping as well. Okay. So, these are your set of properties, you can have phonon properties, optical properties and thermal properties. Knowledge of these properties basically tell you how the eventual performance of the device in which you are using this semiconductor might be like. Okay. So, now let us move forward and see what happens when you join two dissimilar semiconductors. Okay. Heterojunction, when we use the word hetero, we are talking about two entities or two materials which are not similar to each other. Okay. So, for semiconductor device application, this difference in energy gap, it provides another degree of freedom that produces lot of interesting properties. Okay. If you make a junction between two similar semiconductors, it is known as a homojunction, but if you are joining two semiconductors, they are semiconductors, but they will have different energy band gap, they will have different phonon, optical and thermal properties. Okay. So, that sort of arrangement is known as a heterojunction. It has very major applications, a lot of modern semiconductor devices rely largely on heterojunctions. Okay. The advancement in the epitaxy technology, the fabrication technology where you deposit a thin film on a large relaxed substrate, produces a lot of electrical improved electrical properties which are used in very major semiconductor devices. Okay. So, epitaxy technology can be used to grow lattice matched semiconductors, or it can also be used to grow a mismatch, two mismatched semiconductors on top of each other. Okay. So, heterojunction have been widely used in device applications. The underlying physics is that when you deposit, suppose you have a large substrate, thick substrate, okay, and you deposit a thin film. Okay. So, you have a certain thin film and this is your substrate. Okay. When you deposit a thin layer on a large substrate, the film, the thin film, because of its lower thickness, will tend to copy the lattice structure of the substrate. Okay. If there are two dissimilar materials with dissimilar lattice structures, the thin film on the top will try to copy the lattice structure of the substrate on the bottom. This is going to produce strain. Okay. If the lattice constant of the film is lower, it might try to expand its lattice constant, undergo tensile stress. If its lattice constant is larger, it might undergo compression, producing compressive stress. Either way, it is going to produce lot of interesting electrical properties. Okay. So, lattice constant and energy gap play a very important role whenever we are creating heterojunctions. Okay. If, as I said, we produce strain when we deposit thin films on large relaxed substrates. If the lattice constants are not severely mismatched, you can produce good quality epitaxial layers. Okay. See, the catch here is that the film which you are depositing on a substrate should be of an optimum lattice structure in such a way that it does not, that the strain inside the film does not cause lot of defects. Okay. So, the amount of lattice mismatch and the maximum allowed thickness are actually related. This thickness is also known as critical thickness. How much of lattice constant you can accommodate on a substrate plus how thick the layer can be grown. These two parameters are going to decide the quality of the epitaxial material. In thin heteroepitaxial layers, the epitaxial layer can be physically strained to the degree that the lattice constant matches exactly to the substrate. Okay. So, say for example, if you have silicon and germanium, these two have a difference of about nearly 4% in lattice constant. Okay. The lattice constant of germanium and silicon are different by 4%. Whenever you deposit thin silicon on germanium, silicon will try to expand because its lattice constant is lesser than that of germanium. It produces tensile stress, okay, or tensile strain, right. This strain alters the energy band diagram, right, provided that the thickness is lower than the critical thickness. Okay. Above critical thickness, the layer, the strain is going to become 0 and you are going to have full relaxation, okay, and we do not want that. We want strain to be present. So, when silicon tries to become tensile strained, it develops, it alters the energy band diagram, okay. It reduces the band curvature, which enhances which affects the effective mass, lower effective mass, and it increases the mobility of charge carriers. So, strain in heterojunctions tends to produce high mobility devices, right. So, the degree of lattice mismatch can be defined as this is the mismatch. Okay. So, you have the epitaxial layer lattice constant minus the lattice constant of the substrate, you take the absolute value, okay. One might be lower than other. So, you take the absolute value divided by the lattice constant of the epitaxial layer. That is how you measure the amount of mismatch between the thin layer on the top and the substrate at the bottom. And half of this lattice constant of epitaxial layer is the thickness which you can have. Okay. This is the amount of thickness which you can have for the epitaxial layer, so that it does not relax itself. Okay. This is how the graphically or pictorially you can say it looks like. So, you have two materials, right, which are being grown on top of each other, and if the lattice constants are different, you produce strain in them. Okay. Now, how do we classify these heterojunctions? The energy band diagram helps us to classify it. The heterojunction, okay, if I draw again, the heterojunction looks something like this: a thin film on top of a substrate. Okay. This is a heterojunction. Okay. The substrate is relaxed, it does not have any strain, and the film is expected to be fully strained. Okay. This is known as a heterojunction. It can be classified into three types, right, type 1, type 2 and type 3. Type 1 is also known as straddling heterojunction, type 2 is also known as staggered heterojunction, and type 3 is known as broken gap heterojunction. Okay. And they can be classified on the basis of their energy band diagram. Different combinations of EC and EV basically tell you which type of heterojunction we have. Okay. We can also use the concept of electron affinity, which is nothing but the distance between vacuum level, your so called reference level, and the conduction band minima, EC, start of conduction band. Okay. So, different values of electron affinity also helps you to differentiate between different heterojunctions. So, in type 1, the material will have lower EC and higher EV. Okay. A type 2 heterojunction, the location of lower EC and higher EV are displaced with respect to each other. So, electrons at lower EC and holes at higher EV are confined in different small spaces. In type 3, which is a special case of type 2 only, the EC conduction band minima of one side is lower than the valence band maxima of the other. Okay. When we say one and other, we mean the two materials, EC and EV of the film and EC and EV of the substrate. Okay. So, in type 3 you can say that the conduction band basically overlaps the valence band at the interface, that is why we say broken gap heterojunction. Okay. Pictorially we can see it like this, that this is your type 1 heterojunction, okay, and this is the type 2 heterojunction. So, in type 1 you can say that it has lower EC and higher EV, a smaller energy band gap. Okay. So, the band gap here, say let us call it E1, and if I compare it with T2, the lower EC and higher EV, they are basically displaced. Okay. So, the minima of EC and maxima of EV, they are actually displaced. So, if I measure the energy band gap, this E2 is usually higher, and in type 3 at the junction they basically overlap. Okay. So, it is difficult to identify where the energy band gap is, right. So, with this we will conclude our today's lecture. These are some of the sources which you can go through to see the content covered in today's lecture. Just to summarize, we have studied some of the theoretical properties associated with different semiconductors like optical, thermal and phonon properties. Plus we have analyzed how a heterojunction, a junction between two dissimilar semiconductor looks like. When you produce such kind of heterojunction, you introduce strain, which tends to produce very high mobility devices and is quite useful, provided you do not exceed the critical thickness of the strained layer. Okay. So, with that we end our today's lecture. Thank you for watching.